So as mineral processors perhaps don't give stockpiles enough attention, but stockpiles are incredibly important to the operation of mineral processing plants. If we consider the coarser stockpile, the stockpile is the buffer that decouples the mine and the plant, and therefore it increases the availability of each. And properly operated, the stockpile can blend ore or properties to iron out fluctuations to give a more consistent feed grade and size to the plant. And this should result in a more stable milling and flotation performance. But there's also complex flow within the pile and segregation by size that even if the feed to the pile is uniform, could induce variability in the stockpile products. So we need to be able to predict and model this. Also, increasingly, we're collecting richer geometallurgical data from the mine. But if we want to use this data for plant optimization and control, we need good models of stockpile behavior to track it. So I just want to quickly point out a couple of aspects of stockpile design. Coarse ore piles are usually fed from an elevated conveyor. And underneath, we usually have multiple apron feeders for extracting ore onto one or more conveyors. Commonly, these conveyors feed SAG mills. And also note that only material in an inverted cone above the feeders is live. So large regions around the feeders are dead volumes that can't be drawn down by gravity. So if you want to access it, you need to push this in with bulldozers or the like. And this dead volume can often be 50 to 80% of the total pile volume. For the most part, we usually have very little information about the state of the stockpile in real time. We may have an estimate of the stockpile volume or level, and on well-instrumented sites, we may be measuring on-belt size distributions on the product conveyors and maybe the feed. But we rarely have proper models of the stockpile that can help with process control. Simple 1D queuing models like the first in, first out are sometimes used. This might be better than nothing, but it ignores many aspects of stockpile behavior, especially if you have multiple discharges or where segregation is important. With recent developments in drone LiDAR or photogrammetry, we now have powerful tools for stockpile mapping and gives you very accurate measurement of stockpile volumes, but these measure the surface profile and they're not able to track the properties of what's inside the pile. And also these measurements that tend to be relatively infrequent, such as weekly. Many researchers have also been trying to solve the problem of stockpile simulation using DEM, but stockpiles remain a challenging problem for DEM and other numerical simulation tools because of the sheer number of particles. To date, DEM simulations are still quite slow in this application and only allow relatively simple piles to be simulated. A mathematical technique that's largely been overlooked in mineral processing is called cellular automata. And pioneers of this method include John von Neumann, John Conway, Per Buck, and Stephen Wolfram, and developed these techniques. And a lot of the early CAs focused on elementary CAs, which just store an integer or Boolean state for each cell. In general, the grid cells interact only with their immediate neighbors via simple local rules, rather than necessarily using a physics-based approach. In contrast, force chains in DEM can potentially connect all of the particles in the pile, but require much more computation. An important characteristic of CAs is that even with very simple rules, we can see complex and interesting structure emerge when these local rules are applied to the entire system. Some successful work has been done in mining to simulate granular systems in block caving, for example, showing that the method can be useful in industrial applications. And the chief advantage is that these simulations tend to be very fast. In our implementation, we use an extension of CAs called continuous cellular automata. We set up a 3D grid, and in each grid cell, we store multiple properties. This includes an integer state describing the cell type. At the bottom, in red, you can see static or base cells, and these are blocks that ore cannot flow into. So we use these, for example, to define a sloping bottom of the pile. For the remaining cells, the cell type can change during the simulation from being empty, such as the white cells at the top, to part 4, which are the blue ones at the surface of the pile, and the full cells in green in the middle of the pile. Each cell can also have a filling between 0 and 1, and this feature for part-filled cells allows the pile to have any angle of repose we want. Each cell can also have a characteristic size, or D80. The cells can also store grade or some ore type data. And we can also store the time when the contained material was first added to the pile. So this can track the age or residence time. If necessary, we can extend this set of properties as well to include moisture, density, or other things depending on what's needed. Then in each time step, we can follow 4 calculation steps that I'll detail in the next slides. So the first step involves adding a small amount of ore to the pile. So we estimate the position of the pile where the fresh feed is added using a trajectory model, for example, if it's from a conveyor. And stockpiles are usually fed from a conveyor, tripper, or stacker, and this feed point can vary over time as well. So depending on the state of the pile, how it's drawn down, the material can be landing on one side of the pile or the other, as you can see in these videos. We can also factor into the model the observation that feed from the conveyor can become segregated. So you can see in this video here that the coarse particles tend to ride on the top of the conveyor and therefore gets preferentially thrown to the far side of the pile. This mechanism results in the pile being biased with respect to particle size, and it's called trajectory segregation. So in our model, we split the feed into a coarser and finer fraction using a segregation model, which I'll discuss later. And in a given time step, the feed rate corresponds to a certain volume in the simulation. This volume is split across 2 increments that are added to the pile in adjacent columns, a coarse fraction on the far side and a fine fraction on the near side. We combine the properties of these feed increments with the properties already at the surface cell where they land. When this is done, there's a high chance that the height difference between these columns and the surrounding columns exceed the angle of repose, and therefore the surface is unstable. Steps 2 and 3 involve the discharge and propagation of the ore as material is removed from the pile at the base. So during each time step, we need to subtract a small increment of ore from one or more designated draw point cells. Because the time step is relatively short, the draw point cell doesn't empty every time step, but when it does, the cell becomes empty and it triggers a propagation rule. In the simplest case, we can calculate the probability of one of the 9 cells above that draw point cell, which is now a void, to drop into that empty cell. One way to do this is to say that the probability is proportional to the inverse distance between the cell center points, as used by Castro. And if we make this assumption, we get this probability map describing that probability. Once that cell has been selected to drop into the void cell, it creates a new void in the layer above, and we simply repeat this rule until the void reaches the surface of the pile. And this creates this random zigzag path. Again, at the end of the process, the surface of the pile is potentially unstable with respect to the angle of repose. Here's a cross-section through a 3D simulation that starts with layered bands. And if we discharge over many time steps without adding new feed, we get this movement of ore that resembles a column of mass flow, but with a degree of mixing. And this is similar to what we see in granular bin flow experiments with free-flowing materials. The final calculation in each time step is to ensure that the surface of the pile is stable with respect to the angle of repose. To do this, we randomize the order of the columns so that we calculate every column in the grid once. And for each column, we find the maximum slope to its 8 immediate neighbors. And if the angle of repose is exceeded, we calculate how much material should flow from the high column to the lower column to restore the angle of repose. If the properties of the material that flow from the high to the lower column, the properties of the material that flow to the lower column are then combined, and we repeat this for all of the columns in the grid. But we know that whenever we have a mixture of dissimilar sized particles in movement, they tend to segregate. We see this, for example, in rock piles, in DM simulations, and in this toy experiment. The coarse particles tend to concentrate at the outside and the fines in the middle of the pile. The dominant mechanism causing segregation like this is called sifting. So basically, fine particles sift or percolate between the gaps of the larger particles, and this especially happens when the material is in motion. So we've modeled this mechanism with a simple segregation function with 3 parameters represented graphically in this plot. The parameters need to be tuned for a given granular system. The first parameter is the fine size. When a region in the pile only contains fine particles, segregation rate slows down. Likewise, when a region in the pile only contains coarse particles, coarser than the coarse size parameter, the particles can't percolate between each other, so segregation rate reduces. The final parameter essentially describes the breadth of this lens shape. So here's a mock-up example where we start with the material in the upper column, having a D80 size of 70 millimeters, and the lower cell has a D80 size of 75 millimeters. The upper portion segregates into 85 and 55 millimeters via this segregation function. And the 85 millimeter portion flows to the lower column and combines with the existing material to make it 80 millimeters size in the lower column, leaving behind 55 millimeters in the upper column. So now the lower column is significantly coarser than the upper column. So this process is repeated for all of the surface flow events, and eventually you get a segregation appearing. So for calibrating the 3 segregation parameters, we simply do a laboratory experiment by forming a conical pile using scaled down particles that match the feed size distribution from the plant. We then use a specially designed cookie cutter device to sample the pile and measure the particle size distribution for each of the concentric samples. Once this is done, we can simulate a conical pile using our scale stockpile model and tune the parameters to achieve the right amount of segregation. The parameters are scalable, so we can use these parameters for the full-scale simulation. Now let's apply the model to simulate real stockpiles. The first case study is of the coarser stockpile at Las Bambas in Peru. It's a large pile with about 105 kilotons live capacity, or about 18 hours of production. The stockpile is fed from the right, and at the bottom are 2 rows of apron feeders to feed 2 sag mill lines at this interesting angle. We've obtained almost 2 months of data at 5-minute intervals from their PI system, which included the feed tons, the feed size from on-belt split cameras, tons per hour on the 2 SAG feed conveyors, and the feeder speeds on each of the 8 feeders. So these were all model inputs. In addition, we got stockpile height and product size on both of the SAG feed lines for model validation. We also performed the lab segregation test to obtain the segregation parameters. So the simulated stockpile is made of a grid containing about 80,000 cells, each of 3 meters in size. Those arrows there before showed the locations of the conveyors, and the cells are colored by size. So this simulation uses a 6-second time step, and notice there's an octagonal pyramid shape, which is the result of the assumptions in the surface flow step that consider only the 8 surrounding columns. Here, we've assumed that that we have a constant angle of repose. Notice also how this sifting segregation causes the periphery of the pile to become coarser, and the trajectory segregation mechanism causes the right-hand side of the pile to become coarser. To give you an idea of the simulation speed, this simulation over a period of almost 2 months using a 6-second time step takes about 20 minutes. Rather than a fixed angle of repose, we could also make the angle of repose a function of particle size, for example, as in this simulation. The level sensor on the stockpile is located slightly off center of the stockpile, and the model, which is the orange line, does a good job of predicting the stockpile height at the location corresponding to the level sensor, which is the gray line. And the highest point on the pile is the blue line. Because we're only using the tons in and tons out for this simulation, we expect to see some drift over time in the level response. And this plot shows a period of almost 2 months. So, and you may be able to see that there is an offset that's developing towards the end of the simulation. So essentially, we do need to periodically calibrate the model. So perhaps on a weekly to monthly basis, or more frequently if stockpile dosing is practiced. The model also does a reasonable job of predicting the product size on each of the lines. Looking at these plots, line 1 is coarser than line 2 for both the measured and simulated data. There's a lot more variability in both the measured D80 size and the simulated result as well. So because these points represent the output every 5 minutes, so realistically we need to average over a longer time scale, say an hour or so. The data, if we plot this data in a frequency plot, it more clearly shows this difference between the product sizes from the 2 lines. Line 1 in the blue bars is significantly coarser. And this size bias also has a noticeable effect on the plant performance. So SAG1 has a higher throughput and has a slightly lower power draw, probably due to requiring a lower ball load. The second case study where we applied the model is the Batu Hijau coarser stockpile in Indonesia. It's a smaller pile, but this pile is fed from a tripper that moves back and forth. The pile also has 2 product conveyors that come out at right angles to the feed conveyor. Again, we received about 2 months of production data of the feed rate, the feed size, again from split cameras, the tripper position, discharge tons and feeder speeds. And for validation, we received the stockpile height for model, but we didn't have the particle size in this case. So again, we set up the model simulation with about 150,000 grid cells, with each cell being about 1.5 meters in size. The time step in this case was 3 seconds. Notice that the 3 pylons in the pile have been simulated using the base cells, Again, you can see the segregation around the periphery of the pile, and the feed size occasionally changes during the simulation due to the feed size changing. The stockpile emptied out at that point, and then started up again, and you can see that the stockpile height predicted by the model in orange does a good job of tracking the height from the physical level sensors, which are in blue, and in the upper chart is a roughly 3-week period, and below is a zoomed in section of about 2 days. Keep in mind, this is based also on tons in and out without any other corrections applied. So to run this over the longer term, we still need to make periodic calibration adjustments every few weeks or so. Using the data in that 3D grid, we can calculate other useful outputs that can be displayed in real time. So on the left is the total and live capacity of the pile, and on the right is the live capacity above each of the 6 apron feeders. In this case, the 2 middle feeders have by far the most live capacity most of the time, and I think this kind of information can be more useful than simple level indications for managing the stockpile. We can also calculate the D80 above each of the apron feeders, and potentially this information could be used to set the feeder speeds and to optimize the feed size to the sag mills. So you could draw more coarse material if you wanted, or more fine material, if depending on the load level in sag mill. Similarly, we could show other details such as residence time or grade if we were tracking these properties through the pile. The model's flexible enough to be used to simulate a wide range of stockpile and bin designs. So in the previous examples, we had flat bottom piles except for a few pylons supporting the conveyors, but we can have a base of any profile, such as a sloping base, which might increase the live capacity of the pile. Here we're initially feeding the pile, then we start discharging, and finally the feed turns off and the pile empties out. Another application for the model is to simulate silos and bins. The grey cells represent the conical base, and the visualization is slightly different, but it's the same process. The bin fills up, then the discharge begins, and the feed stops, and the silo empties out. And you can see in this case, the coarser material had rolled to the outside of the pile, outside of the bin, and so there is segregation induced in that pile. Multi-outlet bins are also quite common in the industry for feeding various equipment. So some time ago, we were doing some sampling work and sampling conveyors around a bin that had this kind of arrangement with a central feed and 3 outlets. And what we saw in the mass balancing was that the outside feeders were significantly coarser on average. Now with this simulation capability, we can see how the segregation is causing this behavior, and yeah, so we can explain why the segregation takes place in that design. For a better, perhaps more costly way of designing such a bin would be to use a tripper or shuttle conveyor. This way, each of the bins feed a much more uniform feed. So we can simulate these kinds of designs as well. And we would, of course, be happy to try simulating even more complex designs. With this capability, how can we use this stockpile and bin model, and what other research do we have to do? So we've been able to show that the model can be linked to live process data, and therefore act as a soft sensor for real-time modeling and monitoring of the process. And as shown earlier, we can estimate a real-time view of the surface profile and level at any point on the pile, total and live tons, tons, size and grade above each of the apron feeders, and residence time, such as you can see in this plot. And we can use this information for stockpile management, for process control, for example, optimizing SAG feed, and potentially for metal accounting and grade reconciliation without having to assume that the entire stockpile is one average grade. At the JK, we have a strong research focus on dynamic simulation and modeling, and the stockpile is now a part of a growing library of mineral processing models running in MATLAB. We're able to link simulations to offline production data as well, and we're working with JK Tech to connect the simulation environment to their JK VBOK blast modeling package and geomet data. So this kind of environment will allow us to link the stockpile model with other salt sensor models such as JK MillFit, and eventually simulate the whole production chain in a kind of digital twin. The stockpile model could also have application in aspects of stockpile design. For example, we could compare designs with different apron feeder placements, base profiles, feed conveyor designs, tripper control logic, and so on, and predict its effect on live capacity, segregation, blending efficiency, and so on. So in conclusion, we think Cellular Automata offers a relatively simple way of modeling complex stockpile and bin geometries, including moving feed points, multiple discharges, profiled bases, and so on. And we now have a fast and practical model for real-time applications in mineral processing and a means to track material flow through the pile. We also think this capability is quite unique and exciting, and that it unlocks new possibilities for process control in geometallurgy. But we'd be keen to hear an industry perspective as well. I'd like to acknowledge my brilliant PhD graduate, Zemin Yi. He was instrumental in developing this model, and he's now project met at Mount Isa. Also, Mohsen Yeye, our director at the JKMRC, who's also Zemin's PhD advisor. JK Tech for allowing me to present today, the mining companies we've worked with so far on this journey, and my colleague Gordon Forbes for helping with data visualizations. And also, we have a brand new publication out that you may wish to check out as well. So with that, I'd like to thank you for attending and showing interest in this work, and I'm looking forward to your questions or comments.